go back and remember how to multiply fractions. And we're going to apply this idea to rational expressions, these more complex fractions that use polynomials in them. Well, before we even get to that, let's just make sure we remember how to multiply fractions together. So we're taking a look at this first example that says 2/3 times 9/10. Right? And when I take a look at an example like this, we're just remembering how do I put these two together using multiplication. So if you remember the rules for fractions, we said if you multiply across the numerators and multiply across the denominators, right? In this case, we would get 18 over 30. Okay? And then the idea was we need to look at our answer and say, is there anything that I can do to simplify this? And in this case, if you remember from simplifying fractions, we said 18 is really 6 times 3, right? And 30 is 6 times 5. So what I'm recognizing is that both of these have a common factor of 6, and I can cancel out that common factor, and I can get an answer of 3/5, right? So if you notice, what we had to do is we put them together, we got larger numbers, and then we had to break down those larger numbers and to find our common factor. So taking a look at this second example, that gets to be a lot more of a problem because 18 times 42 is going to be much larger, and there's going to be lots of different possibilities, and it's going to take me a lot more work. So we had this idea of maybe before we multiply to get these together and get bigger numbers, why don't we break down the smaller numbers that I know a lot more about? Like I can look at 18 and say, you know what, 18, let's scan along the bottom. Well, 18 and 12 both share a 6. So let me break this up into 6 times 3. Okay, and then I'm going to say 7. Well, that's just 7 times 1. There's really no other way to break that down. Okay, and looking at the other fraction, I'm going to do the same thing. I'm going to recognize there's a 7 down here, so I could turn this into 7 times 6. And then the 12, we've already kind of talked about, that's 6 times 2. Right? And so now I can look at this and say the 7's cancel and the 6's cancel. Okay? And I can look at this and say, okay, a 2 and a 6. Well, a 2 and a 6 is, I can break down this 6 even further and call that 3 times 2. And I can cancel out at least this 2 and the 2. And so if I take a look at what's left, it looks like I have a 3 and a 3 left on the top that I have not canceled. So that would be 9. 3 times 3 is 9. And on the bottom, I just have the 1, right? And I can, so again, more simply write this just as 9. So if you notice, I didn't have to deal with the large numbers. I don't even care what 18 times 42 is. I broke them down before I put it together, and then I just gathered up whatever was left over, right, and put that together. And it was much easier. I didn't need to use a calculator. I didn't need to think about factors of some large number in the hundreds or in the thousands, right? We took care of all of that before we put them together. So the second method is how we're going to handle rational expressions, because we get the same problem. If I start multiplying together binomials and trinomials, I get these really complicated expressions that I don't know how to factor. And so if I take a look at this simple problem here, again, it's a bad idea to say x plus 4 times 3x plus 21. I'm going to get a quadratic trinomial, right? And I'm going to get a quadratic binomial on the bottom, and then we'll have to try to figure out if we can factor those. Don't want to do that, right? So instead, what we're going to do is we're going to look at each of these expressions and say, can I factor it? X plus 4 does not factor. It is a linear binomial. 3x also does not factor. It is a linear monomial. 3x plus 21 does factor, though, because it has a GCF in it. So I'm going to remove that GCF and turn it into 3x plus 7. And again, that x plus 4 does not factor. So now I can take a look at this and say, all right, let's see, x plus 4 and x plus 4 cancel. Okay? And I have these 3's here, and I'm wondering whether I can cancel those. And the answer in this case is yes, I can, because this is 3 times something, and this is 3 times something. And our rule for canceling is that we are allowed to cancel factors. And factors are parts of multiplication problems. So because I'm saying 3 times something here, and I'm saying 3 times something here, they will cancel out. So let's take a look at what's left over. I have an x plus 7 on the top. That's it. And I just have an x on the bottom. And so now we need to consider, can I cancel out those x's? Because I do see an x on the top and an x on the bottom. So I'm looking at this and saying, all right, is this x times something? And in the numerator, the answer is no. And so I'm not going to be able to cancel out the x's because I can only cancel out factors, and the x in the numerator is not a factor. It is a part of an addition problem. So I'm going to say this is my final answer. However, I need to state a domain restriction, which, remember, domain restrictions are just what makes the denominators of any part of your problem equal 0, right? So for fractions, domain restrictions are zeros in the denominator. So for 3x, x cannot be equal to 0 because that would turn this into a 0. And for x plus 4, I don't like negative 4. So I'm going to get rid of both of those. So I'm going to say my final answer with domain restrictions is x plus 7 over x. X is not equal to 0, and x is not equal to 4. Okay, so let's take a look at a second example that maybe has a little bit more factoring involved. So if I take a look at this example, there are a couple of factoring things that happen, and we also get a nice little, another thing that we need to consider. So 2x plus 3 doesn't factor, no GCFs. 4 times x plus 6 does have a common 2, so let's get rid of that. This is 2 times 2x plus 3. Okay, and this 4x squared minus 36 actually has 2 steps of factoring. I see a GCF to start. We always check for that first. And it looks like that turns into x squared minus 9. And then x squared minus 9 is a difference of 2 perfect squares, so I'm going to factor it one more time. So this turns into 4, x plus 3, and x minus 3. Okay? And so now I'm going to look at 3 minus x. I'm going to say, you know what, 3 minus x looks a whole lot like x minus 3. They're very close, except they're off by exactly one negative sign. If you take a look at x minus 3, it's got a positive x in the numerator. Okay? And my 3 minus x has a negative x. So I have a positive x and a negative x. They're off by exactly a sign. If I take a look at the 3, the same thing happens. This is positive 3 and negative 3. So let's consider whether we can cancel things that match but are off by exactly a sign. So here's a simple example of that. If I said negative 7 over 7, can we simplify this? Right? And we know that the answer to this is yes. We can turn this into a negative 1. Here's really what you're doing to do that. You're actually saying, you know what, I'm going to pull away the negative sign. I'm going to turn this just into negative 1 times 7 over 7. And now I have my match, right? 7 and 7 match each other, and I can cancel. And there's that negative 1 that we know is the answer to this. So this is the idea that we're going to apply when we look at factors that are off by exactly a negative sign. 3 minus x, if I pull away a negative 1, okay, now becomes positive x, okay, and negative 3. Okay? So that's one little trick that we need to take into consideration, that we can cancel things that are different as long as they are different by only a negative sign, right? Because of this situation right here. So now I can cancel and say, let me get a different color, x minus 3 and x minus 3. Okay? I have a 2x plus 3 and a 2x plus 3. Okay, and I'm taking a look at what's left, and let's gather it all together, and we'll do one more quick step. So I see 4, okay, and an x plus 3 that's left on the numerator, and I have 2 times negative 1 is a negative 2, right? So the one last little thing that I'm looking at is, okay, wait, I have a 4 and a 2, and this is a 4 times, so I can cancel that. So let's do one more little step. 4 divided by negative 2 is just negative 2. Negative 2 times x plus 3. So we want to make sure we simplify as much as we can. Okay? And so just as a reminder, when we're doing our simplifying, we do not need to multiply the negative 2 back in. We can leave it in factored form. If you multiply it out, it's completely okay, but it's not necessary. Okay? So let's take a look at one more problem. Okay? And in this case, we have this situation where we're multiplying together a fraction on the left with something that's not a fraction. And so let's think about how we would do that with numbers. Okay? So if I had something like 3/4, and I wanted to multiply it with, say, 10, we have to think about how do we multiply together something that is a fraction with something that is not a fraction. And the simple answer is we turn the whole number into a fraction by putting it over 1. So really the 10 is the numerator that I'm going to compare with the 3. Right? So let's get rid of this and let's apply this to our algebra problem. Right? We're going to say this 2x squared plus 14x plus 24 is really over 1. Okay? And so now I'm going to go through my factoring, and I'm going to make sure that this ends up in the numerator. So our 3x does not factor. Okay? X squared plus 3x plus 4 is a quadratic trinomial, so that's in this case going to be x plus 4 and x minus 1. Okay? And again, this is one of those expressions that factors twice. We're going to first pull out a 2, right? X squared plus 7x plus 12. And then this multiplies into, factors into x plus 4 and x plus 3. So this is 2 x plus 4 and x plus 3, and it's over 1. Okay, so let's do our canceling. And in this particular example, there's only one factor that cancels. So we're going to say the x plus 4 and the x plus 4 cancel each other out. And so let's put everything together. So I see 3x times 2. That's really simple. Let's put those together. That's a 6x. Okay, and I have this x plus 3, 6x times x plus 3, over x minus 1. Okay? And my domain restrictions would be a negative 4 would give us a problem. Okay? So x cannot be equal to negative 4. And a positive 1 would also give me a problem. So I'm going to make sure to tell people, do not use those values. They will give you a 0 in the denominator. So our final answer, okay, is this expression 6x over x plus 3, 6x times x plus 3 over x plus 1. X is not equal to negative 4, and x is not equal to 1.